It's time for one of my very few lectures because I haven't found anyone else who's explained these parts all together in a way that will be really useful for you in understanding chemistry. So the first part you've learned before. Opposite charges attract. And if you have big opposite charges, they attract more than small opposite charges. And we're going to add partial opposite charges with this little symbol delta plus and delta minus. Now that's less than plus 1 and less than minus 1. These are partial charges. So they attract even less. Of course, like charges repel, but I'm not going to worry about those. Okay, so memorize this. Let's add a second thing. If two charges are close together, they attract more than two charges that are far apart. Okay, now that you've got this, we're going to go to why everything attracts in chemistry. We've got charges. You could have something like a +4 and a -3, or a +1 and a -1, or we could go down to a partial plus and a partial minus, or we could have a smaller partial plus and a partial minus. Or we could have charges that exist only temporarily. And maybe they're very small. And you can see how these at the top would give a strong attraction, and the charges down here at the bottom would give a weak attraction. In fact, you might call it very weak or very, very weak. All of these things exist in the molecules you've been learning about. You've got ionic bonds, where the ions have full charges that can be over a whole range. We have hydrogen bonds. Dipole-dipole attractions. And then the weakest ones here are dispersion forces. It's often called London dispersion forces after scientists who described them. Okay, so we've got all these kinds of intermolecular forces. We've got these intermolecular forces, and they have charges associated with them. Now, you've been learning about organic molecules. And you can categorize your functional groups by where they fit in these different types of bonding. You could have something like, maybe you'll occasionally encounter a phosphate group. Or it might be bonded to some organic molecule. And will only have a -2 charge. But there are only 2 organic functional groups that we've seen with charges. We've got positive charge when we have an ammonium group. So we've got an amine that picks up an extra H+, that can have a positive charge. And then we've got a carboxylic acid that can lose an H+ and become a carboxylate. With a -1 charge. Hydrogen bonding. We get that whenever we have an N or an O or an F, as you've learned in your previous classes, bonded to an H. And then it can form hydrogen bonds. So we're going to look at hydrogen bonds. Our groups that we've seen are alcohol groups, amines, as long as they are primary or secondary. But we've also got carboxylic acids, with their double bond to O and their OH. We've got amides. I'll draw it skeletal with those 2 NHs. Now each of these has lone pairs of electrons. And those lone pairs of electrons can act as acceptors for the hydrogen bonds. And the H's, the NH, the OH, those are donors. All right. Functional groups that do dipole-dipole. Anytime we've got a CO bond, like with a ketone, or an aldehyde, we can have dipoles. You can have weak dipoles with something like an ether. Now, I haven't covered every functional group, but you can go through your functional groups and look for these OHs and NHs and categorize them with hydrogen bonding. You can look for COs or CNs and categorize them as dipolar molecules. Now, in organic chemistry, we're going to split these dispersion forces. I'm going to split it into 2 groups. Aromatic and aliphatic. When you've got an aromatic ring, these forces arise from electrons moving within the molecule. When you've got an aromatic ring, the electrons are shared all around it, and so they have farther to move, and you can get some interesting effects. These are called pi interactions. And then we've got these basic dispersion forces with the alkanes. But when you put these in water, they like to stick together very well, so we describe something as the hydrophobic interactions. And those become very important in biochemistry because everything is in water. So London dispersion forces that are very, very weak and generally not important in organic chemistry compared to when they're compared with these other strong interactions, when you put them in water, they become very important because of how they interact with water. Okay, so I'm going to summarize this again, bring it even in smaller. We've got ionic, hydrogen bond, dipole, pi-pi, and I'm just going to call it nonpolar here. So up here we had these charges. We had a plus, we had a minus, we had a partial plus and a partial minus. Same with dipole. And here we've got temporary partial plus and partial minus, and very small temporary partial plus and partial minus. So we have the size of the charges. Let's look at the distance. The distance between these two is half an ion on each of those. So depending on how big the ion is and how much its charge is, the strength of the ionic bond will vary, but they're about half an ion apart on each of those. On the hydrogen bond, we've got the partial plus. Well, let's draw something. We've got something like an OH going to another O. And the distance here is close to half an atom. And the same here, half an atom when they're touching, as liquids and solids usually do. But these are small atoms. So the distances are quite short for these hydrogen bonds because hydrogen is the smallest atom that forms bonds. Compare that to a dipole. Here maybe you have an O interacting with another C double bond O. And so this adds up to one atom, just like half and half added up to one atom. But in this case, they're not as small as hydrogen. So the distances are farther and the attraction is less. With pi systems, it's not quite so simple because the contact is still CH to CH, but the groups are bigger here and smaller down here as far as distance, but the relationship's not as straightforward as up here. So I'm not going to go into it further because I don't understand all the nuances. I want to add something up top. We've got a stronger type of bond than ionic bonds, but it's inside of a molecule. It's covalent. Here, you've got negative charges in the middle, say a couple of electrons in a bond. And then you've got the core of the atom, so these are the valence electrons in their cloud. And they're shared between two clouds. And the positive charge attracting them is the core charge of an atom. So if it's a carbon, the nucleus, of course, has more than a +4 charge, but it's surrounded by a couple of first shell electrons, and we'll bond that to another carbon. And you can see in this case, we've got a +4 attracted to a -2, attracted to another +4, and the distance between them is very small. The distance between them is less than 2 half atoms touching, because these 2 half atoms actually overlap. So could say it's less than, well, the distance between the plus and the minus is only 1/2 of an atom. So it's twice as close as, say, this oxygen to this hydrogen. Now we're talking just from the valence electrons to the core, a distance of half an atom. So you can see how bigger charges, +4 and -2, and shorter distances make these covalent bonds very strong. All right. We've got to move on to mixing. When you have a whole bunch of molecules, I've got a whole bunch of water molecules. Just going to draw a couple of them. They've got their hydrogen bonding going on. And now I try to mix in another molecule, like methane. Methane and water will mix because everything mixes. If things can move, they're going to mix. If your atoms or molecules can move, they're going to mix with each other. This is a result of entropy and our second law of thermodynamics. So things that move are going to mix, but for some reason methane doesn't like to mix with water. And the reason is water attractions keep out the nonpolar weak attractions. So the stronger attracting force likes to stay stuck together and doesn't want to be replaced with here we've got a very weak dispersion force. So if we break up a strong bond and replace it with a weak one, that strong bond's going to want to reform as soon as they move around and come in contact with each other. So water attractions or stronger attractions are going to keep out things that are just attracted in a weaker way. So what does this mean? So we've got our ionic molecules, our hydrogen bonding molecules, our dipole molecules, and our nonpolar molecules. And you've got your different functional groups. Well, what if we want to dissolve those in water? Hydrogen bonding things have the same kinds of interactions, and everything wants to mix, so yes, they will dissolve. Many ionic molecules also dissolve, but some don't. So there's a range from yes to no for ionic, but most ionic molecules will dissolve in water. You'd have to go back to your solubility rules to find out ones that don't. Turns out most dipole molecules dissolve in water. But nonpolar molecules, only the very smallest amount will dissolve in water, so they're insoluble in water. What if we move to a polar solvent? It's got that ketone in it. It's a polar solvent that can form dipole bonds. Well, that's going to dissolve other polar molecules very well because the bond strengths are equal, and so the mixing takes over. Turns out lots of nonpolar molecules will dissolve in acetone. That's why it's good for removing nail polish. There are a few that acetone won't dissolve so well, but for the most part, nonpolar molecules will dissolve in acetone. You can also dissolve water in acetone. Things that hydrogen bond have a similar enough strength of interaction with the dipole. They can actually donate hydrogen bonds and acetone will accept them. So yes, they'll dissolve, but ionic molecules the ions attract each other too much and won't let the acetone in to separate them. So you can't dissolve salt in acetone. Let's move on to a nonpolar solvent. Nonpolar molecules will dissolve in nonpolar solvents. Polar molecules, some of them will, some of them won't. Hydrogen bonding molecules do not like to dissolve in polar solvents. And of course, ionic molecules don't either. The bonds between two ions are just too strong. That attraction is too strong. It won't let in the nonpolar molecules. So here's our solubility chart. And at this point, you have all the information. I am going to silently draw this in not as fat a font, so you might have to have it on a big screen to see it all. But I'm going to draw all this again, all in one place.